So the next speaker is Masataka Ebara. He's a PhD student at the Kyushu University in Japan, and he will talk about analysis of fatigue crack configuration, influence on the fatigue life.
Thank you, Mr. Chairperson. Hi everyone, I'm Masataka Ebara from Kyushu University in Japan. I will now start my presentation. I'd like to talk about analysis of fatigue crack configuration influence on fatigue life. Here is the background slide about classification of small cracks. Until now, small cracks have been classified by measuring surface crack growth rates, as shown in this table. Mechanical effect is small but exists for microstructurally small crack, whereas microstructural effect is small but exists for mechanically small crack. So, we propose new definitions for small cracks by predicting fatigue loss life from analyzing crack front shapes. And we want to classify small cracks by the scattered existence of fatigue loss life. As shown in this table, for microstructurally small crack, the scatter exists, whereas for mechanically small crack, the scatter does not exist. Here is the assumption slide. Why do we consider such classification is possible? We focus on the crack front shape, not the surface crack length. And this figure shows the crack front shape of an actual inner crack. And here, we propose new concept, restoration force. Restoration force is the main crack prevents local crack from growing. And this figure, this schematic shows a modeled crack of an actual inner crack, and this figure, this schematic shows restoration force. So we can see the influence of restoration force from the strength of local cracks driving force. And next, we prepare two cracks, and these cracks are equal in radius, but crack front shapes are different, so local FCGRs are different. And if restoration forces are strong, we consider these cracks are likely to grow to the same size with the same number of cycles. And here we propose new crack length, L1. L1 is the fatigue crack length at which the fatigue growth life does not scatter, even if the local FCGRs are scattering. And even when the surface crack length of the specimen was measured, the existence of L1 cannot be known. The reason is why scattering local FCGRs is no problem for L1. And therefore, in the materials that have the same material factor affecting L1 value does not scatter. It means reduction of safety factor. And next, here is the approach slide. We want to quantify two factors affecting local FCGRs: microstructural factor and mechanical factor. In each crack, for local crack size, shape, number, placement, and close to out of frame direction are different. So, microstructural factor dominates variation of crack front shape, and mechanical factor is driving force for crack front growth. Quantification is difficult considering many microstructural factors, so in this study, our approach is crack growth simulation of a simple crack front shape using finite element method. And there are several types of crack front shapes. A crack with many local cracks and a clock with some local clocks in places that do not affect each other. And the clock that growth of each clock tip is determined only by the front microstructure placements, and so on. In this study, we focus on this type clock. And next, here is the assumption slide. This is a modeled initial clock, and we simplified this clock. This is the three-dimensional initial clock model, clock 1, and the radius of main clock A0 is 5 times the radius of local clock B0. And these are the assumptions for local clock. Shape is semicircle, growth direction is in plane, number is only 1. By the way, for the material to be analyzed, grain size is set to 50 micrometer, and local clock size is set to half the grain size. So, clock 1 is assumed as small clock. And therefore, these are the assumptions for fatigue clock growth simulation. Analytical condition is a small scale yielding, and FCGRs follow Paris law. To advance discussion. And next, I explain the analysis method for calculating stress intensity factor K. To calculate a known K, I prepare a clock which K is known. And this silver line is analytical solution, and this purple line is exact solution. And when the messing near the clock tip, these red squares is the same for the two clocks, we consider the error between the analytical solution and exact solution as the same R0 is nearly constant in the two clocks. And here is the validation of the analysis method slide. Clock S, which K is known, is a penny-shaped clock and radius is 1 micrometer. And clock T, which K is unknown, is a penny-shaped clock and radius is 10 micrometer. And at R0 was 0.02 micrometer, analytical stress sigma S was 1006 megapascal. And analytical stress sigma T was 3036 megapascal. And then exact Ks value is 0.395 megapascal root meter, and exact KT value is 1.249 megapascal root meter. So, analytical KT value by using this analysis method was 1.192 megapascal root meter. And then the error between analytical KT value and exact KT value was 4.55%. Therefore, this analysis method is viable. And this schematic shows FEM analysis model of clock S, for example. And the analytical conditions are as shown here. And these schematics show overviews of the analytical models and corresponding meshing around the clock tips. These red line are clock tips, and here is the clock surface. And these schematics shows FEM analysis model of clock 1. The analytical conditions are as shown here. And here is the analysis method for fatigue clock growth simulation. We group clock 1 by analyzing stress intensity factor and calculate dAdn times delta n at each point by using this table. And we ended the analysis when the difference between stress intensity factor at point A and stress intensity factor at point B becomes within 5%. And here is the result slide. This graph shows the relationships between stress intensity factor K and number of cycles N. From the result, we found Ka was larger than Kb throughout the analysis. And furthermore, the total length of crack growth at point A was smaller than the radius of local crack B0. And next, in this study, we analyzed case study crack. So to increase the generality of the results, we propose these non-dimensionalization equations for stress intensity factor and number of cycles. Therefore, it can also be evaluated when crack size or external force changes. And next, here is the discussion slide. Why Ka was larger than Kb throughout the analysis. In these schematics, the X mark is the point where distance between crack surface is the longest. So the distance between point A and X mark is shorter than that between point B and X mark. And furthermore, regarding the radius of curvature, main crack is larger than local crack. So, when crack 1 is observed from XZ plane, CTOD at point A was larger than that at point B. So, Ka was larger than Kb throughout the analysis. And furthermore, we found restoration force exists. And next discussion. What kind of crack growth can L1 exist in? This is crack 1. First condition. From the result, before local crack is taken in by main crack, no new local crack occur nearby the local crack. And second condition, no matter how local cracks occur randomly, the fatigue growth life will not scatter. So, for above phrase, L1 exists. And here is a summary slide. Summary. Because of Ka was larger than Kb throughout the analysis, we can say restoration force exists. And there is L1 for the crack front shape analyzed in this study. That's all. Thank you for your kind attention.
Thank you very much. Yes, we have 2 minutes, so if you want 1 or 2 questions, quickly. Yes.
Thank you very much for interesting presentation. First of all, I would like to know what subjects of your consideration, only penny shape crack or more general cases is surface semi-elliptical cracks? Because first slide was surface crack, semi-elliptical forms, and another slide is concerned to penny shape crack. What the subject of your consideration? Penny shaped crack.
Right. His question means main crack and local crack shapes penny shaped semicircle.
So, I am going to the next question. I understand that the subject is penny shaped crack. So, how it possible to parameter L1 to take into parameter L1 to take into account the change of aspect ratio? For instance, penny shaped cracks take place as only -1 R ratio pure bending. As usual, general situation when the aspect ratio, that is the ratio between semi-axis of penny shaped or semi-elliptical cracks, that is a function of number of cycle of loading. And is it possible to take into account by using parameter L1 to change of aspect ratio in general case?
Quick another question, quickly? No? So for the end of the session, thank you very much.